ID number 10685604, answering exercise 25. In this exercise, we are asked to find an isomorphism from the group S square, the symmetries of a square, to a matrices group, a 2x2 matrices group. As you can see, I'm going to call this isomorphism F, and I'm going to refer to the matrices group as group G with binary operation star. Underneath here, I've listed S square, the elements of S square. S square contains the identity, 3 rotations, 4 reflections. I've written the rotations above for reference and the reflections beneath for reference, but we'll refer to them as R1, R2, R3, A, B, C and D respectively in the Cayley tables and all my further workings. The first thing we know is because S square has 8 elements, G must have 8 elements in order for this isomorphism any isomorphism we propose to exist. We also can notice a pattern about the orders of the elements in S square. Obviously, it goes without saying that our identity is of order 1. We've got 2 elements of order 4, that is R1 and R3. And we have got our 3rd rotation and our 4 reflections that are of order 2. Equally, we notice a pattern with inverses. By nature of being order 2, the R2 and the 4 reflections are their own inverse, but R1 and R3 are the other's inverse. So in other words, we could call a subgroup of GR, and R would contain E, R1 and R3, because R1 is R3 inverse and R3 is R1 inverse. What can we say about G? G is a matrix group, a 2x2 matrix group with binary operation that we're calling star. I have proposed this 8-element group for G, which contains the identity to meet the identity axiom, the 3 appropriately chosen rotation matrices, because remember we can consider our vertices of a square as points in a plane, so we choose theta equals 90, theta equals 180 and theta equals 270 respectively, and the 4 appropriate reflection matrices as well, with the same sort of considerations, i.e. for that reflection we would be considering a reflection matrices that reflects a reflection along the line y equals x, etc. For simplicity moving forward, I have given the matrices capital letters. So the identity will be referred to as I, which is standard, and then the other 7 matrices have all been given appropriate capital letters, E, F, G', H, J, K and L. We are going to propose that our binary operation star is matrix multiplication. As shown below, 2 diagonal matrices times together will be a diagonal matrix. This property is also shown by adding diagonal matrices, but what it's worth noting is that our entries of our diagonal matrices are exclusively 1 or minus 1. If we are adding, that does not show closure. So if we're multiplying here, any combination of 1 or minus 1 is 1 or minus 1. If we're adding, that's not the case. Also, we note that the size of G is the size of S square, which bodes well for our future considerations. G, to be a group, obviously has to meet the group axioms. We already know it contains the identity, and with matrix multiplication, the identity matrix meets the necessary criteria to be the identity. Here, I've written out the inverses of the matrices, and as you will notice, all the inverses are found in G. Closure is shown by this Cayley table here. So the isomorphism then. Let's first start establish some patterns with regard to our inverses. As we noticed in S squared, there are some interesting patterns of our inverses. So there are 5 elements that are their own inverse, which is consistent with S square. There are 2 that aren't, and of the 2 that aren't, we notice that E inverse is G' and G' inverse is E, which matches the pattern we see with R1 and R3 in the fact that R1 inverse is R3 and R3 inverse is R1. E and G' are also both of order 4. Therefore, our first proposition is that F maps R1 to E and R2 to G'. We note that of the 5 elements that are their own inverse, 1 should be isomorphic to rotation, the other 4 should be isomorphic to reflections. I'm going to show this. I'm going to now consider the patterns in the Cayley table. So, as I've written down here, in the case of S square, for example, the Cayley table can be considered in 4 quadrants. 2 quadrants that exclusively contain rotations, and 2 quadrants that exclusively contain reflections. And we notice something interesting, because rotations combined with rotations make rotations, and reflections combined with reflections make rotations, but any other combination makes reflections. And this pattern is followed the same by the Cayley table of G with binary operation star. In other words, it can be separated into 4 quadrants, and we notice that certain matrices appear in the quadrant 2 and the quadrant 3, and certain matrices appear in the quadrant 1 and the quadrant 4. Let's look back at our table. We have to combine either a rotation with a reflection or a rotation, or either a reflection with a rotation or a rotation with a reflection. Remember, for our isomorphism to exist, the operations have to be identical, and therefore the patterns should be the same, should show the same patterns. So let's consider then combining, or in this case it's matrix multiplying, 2 matrices that are their own inverse. Let's F and H, just because they're the first 2 left on our list that we haven't assigned. If you times them together, you get G. Yeah? G is found in quadrants 2 and 3. In other words, it should be isomorphic to a reflection. Yeah? To get a reflection, we have to combine. Therefore, it implies that either F is isomorphic to a rotation or H is isomorphic to a rotation. And there is only one rotation we haven't allocated that is to say R2. So we know one of them is, but we're not sure. But we can show this. Let's take one of them, let's say H, and combine it with another matrix that's its own inverse, let's say K. Yep. If we combine H and K, we get E. Yep. As we know, E is our proposed element that's isomorphic to R1. In other words, F inverse is going to map E to R1. It's found, in other words, in quadrants 1 and 4. Which implies if we're saying our operations have to be identical, the only way to get E is 2 reflections combined. Which means that H and K must each be isomorphic to a reflection. Because, by the way, they can't be both rotations, because we've only got one rotation that we've got unallocated. Therefore, H cannot be isomorphic to R2, therefore F must be isomorphic to R2. Because F or H has to be isomorphic to R2. And therefore, our proposal for the third rotation, or R2, is that R2 must be mapped to must be mapped to big F by little f. The 4 remaining elements of order 2 are H, J, K and L. Using our patterns in the Cayley table, we can establish that A is mapped to H by little f, B is mapped to J by little f, C is mapped to K by little f, and D is mapped to L by little f. And therefore our isomorphism in its entirety is here. Our final step to showing an isomorphism is to, using the isomorphism, relabel our Cayley table for S square, and should the Cayley table match that of the group we're trying to map it to, in other words G with star, then we know that they are isomorphic. So that's what I'm going to do now. I've got the Cayley table of S square here, and then I'm going to relabel it here, and then we'll see what happens. So E is mapped to the identity. F, G dash, H, J, K, L, identity, E, F, G dash, H, J, K, L, E, F, G dash, I, J, K, L, H, F, G dashed, I, E, K, L, H, J, G dashed, I, E, F, L, H, J, K, H, L, K, J, I, G dashed, F, and E, J, H, L, K, E, I, G dashed, F, K, J, H, L, F, E, I, G dashed, L, K, J, H, G dashed, F, E, and I. So that is our relabeled Cayley table, and as you notice, this Cayley table is identical to that of G star, and therefore we can say that S square is isomorphic to G, or S square with combination, S square with combination is isomorphic to G with star, where G is a matrix group and star is matrix multiplication, and hence we have shown that this is isomorphism F.